The first way we're going to see how to use our del operator is to take the gradient of a scalar. So if we have the gradient of a scalar field V, that's going to result in a vector that represents both the magnitude and the direction, because of course it's a vector, of the maximum space rate of increase of V. So that's kind of a very wordy definition, but basically what we're saying is that the gradient of a scalar is going to give us the maximum rate of change, so that's going to be the magnitude, and the direction is going to be in the direction of the maximum rate of change. So again, that's maybe a little confusing still, so let's consider some contour lines. So I think that's going to be a little easier to interpret than for instance, going straight to talking about voltages or something like that. So we can consider contour lines, which are indicating different elevations. In this case, let's consider that we have height 3 is our highest elevation, height 2, and height 1 is our lowest. So basically in here in the middle, this is our highest point, and around here on the perimeter, these are our lower points. So we kind of are looking at the aerial view of a hill, for instance. So it turns out we could write our gradient vectors. If we take a gradient at some point along our H1 contour line, we would have maybe a point facing here. Let me do this in a way I can draw it a little easier. So maybe a point here, or a vector rather. And so again, the magnitude of that vector is going to be pointing in the direction of increase, and the magnitude is going to be the maximum rate of increase at that point. So we could have these at any point. And so what we're going to talk about a little bit later is that these are all actually going to be perpendicular to those contour lines. So however we draw them, they're going to be perpendicular to these contour lines. Okay, so in addition to this, so basically we can extend this idea then to sort of quantities that are maybe a little more difficult to visualize, so things such as voltages. We could also talk about electric or magnetic field intensities. So let me just write that as electric magnetic field intensities, because of course our electric and magnetic fields have directions, but we can talk about the intensities in terms of scalars. So with any of these quantities, we can have these gradients which are showing us what the direction is for the maximum rate of change and what that rate of change is. So sort of transitioning now to a more mathematical definition, let's look at how we can take our gradient in our three coordinate systems. So we're going to start as always with our Cartesian coordinate systems. And so oftentimes you'll see shorthand grad V. So again, V is our scalar field. So we can take gradient of V, and what that is that's just going to be del times V. So using our del operator definition from the previous video, we have that in Cartesian coordinates, this is the partial derivative of V with respect to x in our x direction, plus the partial derivative of V with respect to y in our y direction, plus the partial derivative of V with respect to z in our z direction. So that is the definition for our gradient in Cartesian coordinates. So let's now look at our cylindrical and spherical. And so same basic idea, we're just using that del equation from our previous video. So our del V, or our gradient of V in cylindrical, is going to be the partial of V with respect to rho in our rho direction, plus 1 over rho times the partial of V with respect to phi in our phi direction, plus partial of V with respect to z in our z direction. Okay, and then finally for our spherical case, we have that the gradient of V is equal to partial of V with respect to r in our r direction, plus 1 over r partial of V with respect to theta in our theta direction, plus 1 over r sine theta times the partial of V with respect to phi in our phi direction. Now, of course, you don't need to memorize these equations or know how to derive them or anything like that, but you should have them in your note sheets, or at the very least, sort of beyond this class, be able to reference them and be able to use them appropriately. And we'll see how to do that in an example in the next video. So let's talk about a couple of the things that we were kind of qualitatively describing in the previous sort of page up here. Now that we know we can write this gradient v as a nabla v. So our magnitude of this gradient of v, and again this isn't going to matter which coordinate system we're in, so the magnitude of v is equal to the maximum rate of change of v at a point. So max rate of change in v per unit distance. And again, v, keep in mind, is just a scalar field. Okay, we can also say that our vector, because remember this results in a vector, del v is pointing in the direction of that maximum rate of change. So points in direction of max rate of change. And so that's max rate of change in our scalar field v. And then as we saw in the drawing above with our contour lines, that del v at any point is perpendicular to our constant v surface. So at any point is perpendicular to our constant v surface passing through the point. And then a little bit of terminology. We can say that if A, so our vector A, is equal to the gradient of V, then V is the scalar potential of A. Okay, and then so one more thing I want to address here is a directional derivative along a direction. So coming back to our contour example up here, let's say for instance we have 2 points of interest. And so maybe let's say at this point here, let's call this point A. And so let's say at A we have maximum rate of increase in this direction, and of course our magnitude is going to give us what that maximum rate is, and that vector is going to be perpendicular to that H2 contour line. Now let's say instead of in that direction, we want to know the maximum rate of increase in a particular direction. So maybe we have some point B over here. So what we want to know is we want to know along this direction, what is our maximum rate of increase. So what we can do is we can define some unit vector here. And so let me get rid of our dashed line here. We can define some unit vector, so I'm going to call it u sub A, which is in the direction from A to B. So let me just sort of add that dashed line back now. So we have this unit vector. And so what we can do is we can essentially think of it as doing a projection of that blue vector onto our unit vector. And so what we can say then is we can define what's called a directional derivative of v along that, switch back to black here. So directional derivative of v along our unit vector A, and we can define that as del v dot our unit vector A. And again, that unit vector A is our direction of interest. So the last thing we want to do in this video is to define some properties of our gradient. And then in the next video, we'll look at an example and we'll get hopefully a better feel for how to use this gradient, how to use our del operator to find the gradient. So the first property is if we have the del of the sum of two scalar fields, so del of the quantity v plus u, and we basically just distribute that, so we have del v plus del u. Our second property we're going to consider is similar to our product rule. So let's say we have del of v times u, so we have two scalar fields multiplied together. So like our product rule, we have, if we think about taking the derivative of the product of two things, we have the first times the derivative of the second plus the second times the derivative of the first. So here we're going to say v times the gradient of u plus u times the gradient of v. So again, that's sort of like our product rule. And then similarly, if we have the gradient of a quotient of two scalar fields, so v divided by u, we can use something similar to our quotient rule. So our quotient rule, again for derivative, is low d high minus high d low over low low. So sort of translating that here, we have u times the gradient of v minus v times the gradient of u divided by u squared. And then the final one we'll look at is property if we have the gradient of a scalar field raised to some power n. So del of v to the n. And so it turns out that is just n times v to the n minus 1 times the gradient of v. And again, just to be explicit, u and v above are scalars or scalar fields. And in the last one here, our n is an integer. Okay, so in the following video, we're going to look at an example and get a better feel for how to perform this operation with our del operator.